So to understand the conduction of heat, you have to go a little bit more deeper than most videos to understand the experimental data. So I'm just going to go a little bit deeper than normal and start off with the definitions first. So I'm just going to read this out. Thermal conduction is the transfer of kinetic energy through a material. Kinetic energy is the energy of motion, which means the particles in the material have movement, such as vibration. So you can see in this simulation here, I'll just put that on repeat. The particles, if you drop down to here, the heat transfers from high kinetic energy to low kinetic energy. So the particles have a lot of kinetic energy and they're moving and hitting each other, and then they're slowly hitting the next ones to each other and going from right to left. Just as a side note, temperature, we can use Kelvin or degrees Celsius. Because we're doing temperature change, the temperature change will be the same value if it's whether it's degrees Celsius or Kelvin. Just for your side note, you add 273 to Celsius to know what Kelvin is. And we're going to go into detail because we're going to talk about not just the free electrons that can travel from one end to the other, but the other factor that allows something to be a good thermal conductor is if the vibrations of the actual chemical themselves, the lattice itself, the atoms in the lattice, whether they can, those vibrations can move from one end to the other without scattering. So just a quick demo on how gases are very poor conductors of heat. They're very good insulators. The ice cubes are not fully melted through. So the one at the top only has exposure to room temperature air, and the one at the bottom is room temperature water. And they're not fully frozen through, and you'll see after a very short amount of time, one of them melts a lot better, which is in the liquid, and eventually breaks, and the one in the air doesn't break so much. Okay, so it's just to demonstrate that solids and liquids have particles very close together, so their vibrations can transfer heat very well, whereas gases have huge spaces, so it's very hard for those particles to hit each other and transfer the kinetic energy. So gases have a much lower density. If you're looking at values between solids and liquids, density is not that important, and the space between the atoms in the lattice is not that important. They do have an effect. They do help if it's more dense in the smaller spaces, but the electrons that can travel and the phonons are much more significant, and it is highly significant if you're looking at completely different states and not just density within states. Okay, so in this experiment, I'm just putting drops of wax along these 5 metals. They're labeled for you with the approximate conductivity. So watts is the amount of energy per second, joules per second, and that's meters, so length, and that's Kelvin's the same as degrees Celsius. So per distance and temperature increase. So the amount of energy that goes across per distance and degree. Okay, so that's the values. So you'll expect copper to be the best, then aluminium, and then I'm not so sure about the rest. They're a little bit more similar in values. All right. So just giving you an analysis of that. So just putting those numbers here. Now, diamond is by far the world's best conductor of heat, but it has no free electrons. So we'll talk about that later in phonons in the next bit of this video. And so we're just looking at these 5 metals here. Now, copper is by far the best, but it only has 1 free electron, and all the rest have more electrons. And its spacing between the atoms isn't the lowest either. Even in this set, nickel is lower and it has more free electrons. And so it's mainly to do with the free electrons obviously help, but it's more than just that. It's whether that electron can go a distance from one end to the other without hitting another cation or getting scattered. And so it's not traveling from A to B, it's just scattering. And so you can see in this simulation here, you can see that just because you have lots of electrons doesn't mean those electrons can get across. They might hit other electrons or hit other atoms. So it's more complicated than that. It's about the structure of how the atoms are placed in the crystal lattice and how many free electrons there are and whether those electrons are free to move across or not, or whether they're going to hit something else. So it's more than just free electrons. It's about the unimpeded free electrons to travel across will increase its conductivity. So in this experiment, I've just got 1 metal just for reference, but all the others are non-metals, so there's no free electrons at all to move through. And so we're just looking at phonons now. So we're looking at how well the vibrations can move across the lattice. So you've got a simulation of what those vibrations might look like, although they can occur at different angles and in different directions. I couldn't get myself on a handle on a huge diamond, so I've used silicon dioxide instead, which is a similar crystal lattice, but they're not all perfectly even. The graphite itself is not a nice graphite like the simulation either. It would be impure and cut in different planes, so it's probably less than that. So those values are probably reasonable. The rubber is less than 1 for sure, so it should be the worst, and the aluminium should be quite good. What you can see as I go up, so the rubber is about 34, which is the worst. The aluminium's 47, which is the max, and doesn't go much higher because the quartz, as you go up, you can see it goes down to about 42. And the quartz is about 47 as well, and the graphite is slightly lower, which is at about 45. Okay, so if we had diamond, it would be about the same, although it seems like we've reached a max at 47, so we need to do this test at a little higher temperatures and a little longer pieces, I think. But as you can see, this structure here has a smaller atomic bond, but far less thermal conductivity. And so it's more about how the phonons travel across the lattice, which is to do with its three-dimensional structure, and it has a lot to do with impurities and any breaks as well. So not a simple not a simple prediction to know which one it is. Generally, if it has a small atomic distance and it's a uniform, tight structure, it will have allow vibrations to follow through phonons the best and will give a better conductivity. And this is the max value. Diamond is the best that we have. Now, please excuse me for doing this last bit. Science is all about quantitative, using measurements and numbers, not qualitative, which is English. And so I want to do a value and actually calculate a thermal conductivity value. So I'm going to do it for steel because I've got a piece of steel right in front of me, and I'll just put a piece of ice in there and see how quickly it melts. And it's obviously that is terrible because the steel is going to cool down, which it's not allowed to do. And so to make this work a little bit better, I'd need some sort of way to keep it at constant temperature. And so this might be a little bit too much, but anyway, here it is. I'm looking for 50, and so that's the joules per second meters Kelvin. I'm just guessing that the room's about 20 degrees Celsius, the room I'm currently sitting in. I think the ice in the fridge melts at about minus 15, so I'm guessing it's minus 15. These are pretty rough too, the size of the ice cube, and so that works out to a surface area of 3 centimeters cubed, which is that many meters cubed. And that's the formula, which hopefully makes sense. The amount of energy per second, and that the D there is how thick it is. I'm doing it for 1 centimeter. The surface area is here, and the temperature difference is between these two, like 35, but it's obviously a lot less. Okay, and so we are going to be doing specific heat, which is the amount of energy it takes to raise a certain mass by a certain temperature. And so for this one, melting the ice, changing the temperature of the ice, is about this many joules. And so I need to do that for 15 degrees to get it to 0. And so that's the amount of energy it takes to get the ice from minus 15 to 0. And then when you're actually at 0, it's called the latent fusion of ice. You need energy to change it from solid to liquid and vice versa, and that's the number there. And so I've worked out I've got about 3 mils of ice because I've got 3 centimeters cubed, and so that's about 3 grams. So that's how many kilograms that is. And so I need about 1,000 joules of energy as well. So that averages out to that adds up to around 1,100 over that distance, over that time. And that's my final value. So it's 1.5 when I'm meant to get 50. And so the problem is it cools down too rapidly. So I redo it and moving it around a bit. I really should put it on we have a steel stool, which would be better. But I move it around a bit, and then I get to melt a bit quicker, which is 180 seconds. It's meant to melt in 20 seconds, which is possible actually. But also the huge one is the temperature difference. You can see from this simulation here that there's no possible way to stop without actually having more expensive or not just putting all I'm doing is putting a piece of ice and watching it melt. I really can't let the steel cool down.